Okay, so today we want to take a look at solving first order linear ODEs, and we'll solve an IVP as an example. But what do we mean by a linear ODE? So by definition, an nth order ODE is linear if it's of this form. So I could have some, say, a sub n as a function of x, so it's just some function of x times the nth derivative of our function y, which is a function of x, plus, let's say we have an a n minus 1, which is some other function in x, to the n minus 1 derivative. And we can go all the way on and on and on until we say let's get to the first order. Okay, make some constant a1 of x, y prime of x, plus some a0 of x times the function y of x is equal to some other function g of x. So this would be the linear form, or by definition what a linear ODE would look like, provided that an minus 1 all the way down to a1 and a naught and g are all functions of x. They can only be functions of x, not y. And you'll notice that the y's, there's no natural log of y or sine of y. It's just y to the nth derivative, here the n minus 1 derivative, the first derivative. Of course, there's a second, third, fourth, many derivatives in between. And this is the function y. I guess you can say it's the 0th derivative. And then here on the right-hand side, we can have a forcing function of x as well. Since we're only concerned about the first order ODE for now, so for a first order linear ODE, let's go ahead and just keep this back portion here. So we'd have like a1 of x times y prime. I guess I'll drop the x functionality on the y's, plus a naught of x y is equal to g of x. And it makes sense that if I divide everything by this leading term, by the a1 of x, I could write this as y prime plus, now here I'll have a naught over a1 of x, but there really is just some other function in x that I'll call p of x, y is equal to, and then g of x divided by a1 of x is another function in x I'll just call f of x. Okay, so it should be clear here that I'm making the assignment where p of x is just a naught over a1, so a naught of x over a1 of x, and I'm just saying that f of x is g of x over a1 of x. Okay, so they still remain functions in x. Now, it's obvious I have a y prime and a y, and I have to ask myself, I know that when I solve a differential equation, I'm actually looking for a function y of x, but how do I get this, say, y by itself? How do I, if I have a y prime and a y? Well, there's a clever technique, actually, where if I introduce an integrating factor, that's going to be e to the integral of p of x dx. By multiplying this equation through by this integrating factor, let's see, I get e to the integral of p of x dx y prime plus p of x y e to the integral of p of x dx equals my function in x times e to the integral of p of x dx. And really the beauty of the technique is that on the left hand side we really have the product rule, okay, to where I could really write this as an exact differential d by dx of the function, say y, again I'm not writing y of x, times the integrating factor, e to the integral of p of x dx. Okay. And so now I just write out the right hand side. So I have this exact differential here, and then I have f of x times e to the integral of p of x dx here. Well, now I can capture the y simply by integrating both sides with respect to x. So if I integrate here with respect to x and integrate here with respect to x, I have to do the same on the right hand side. But the great thing is that now on the left hand side, I'm just left with y times some exponential function in x, which I can divide out later. It's going to be the integral of that argument, of course, dx. And again, I can divide out this e, and I'm only left with my function y. Okay, so let's look at an example of this. Let's say we wanted to solve 2x minus y, let's say minus y, is equal to y prime. I'll try to make the y's look the same. So y of 2 is equal to 2. Alright, so if I try to put in this linear form, I know that this guy is linear, I wouldn't have selected it, I guess. I get y prime plus y. I just transposed the minus y to the other side and just kind of rewrote it another way. I get y prime plus y is equal to 2x. And so that sort of fits this model where a1 of x could be 1 plus a naught would be 1, and my g of x would just be 2x. Okay? And so now I want to go for the integrating factor. I'll just write that as IF. So since my p of x in this case, like if I compare this to this, y prime plus p of x, y equals f of x, I see my p of x is obviously 1. So I get e to the integral of 1 dx, which just says that my integrating factor is just e to the x power. And if I multiply that through the entire equation, I get e to the x y prime plus y e to the x equals 2x e to the x. And now I know I have an exact differential on the left hand side, so I could write that as d by dx of the function times the integrating factor is equal to, and here I'm just going to write this as 2x e to the x. I'll leave that alone. So all I did was use the product rule here. And the great thing is, again, is that I'm ready to integrate with respect to x. And since I have this exact differential, the first fundamental theorem of calculus guarantees that when I take the integral of the derivative of y to the x with respect to x, I get just the y e to the x. And here I have the integral of 2x e to the x dx. And so the constant come out, but it's clear that I should have just a quick IBP. And here I'll just let u equal to x, du becomes dx, and then I'll let dv pick up the e to the x dx, where v is just the integral of that, or e to the x. Alright, so since I'm writing this as a function u v prime, I'll get 2 times, I guess I could write this as uv, so that becomes x e to the x minus the integral of v du, so e to the x dx. That simply just becomes 2, I guess I could distribute this in, x e to the x minus 2 e to the x, and then plus some arbitrary constant. And I could have waited to, I could have left the this entire piece inside of the parentheses and then distributed the 2, but 2 times c is just another constant anyway, so I'll just leave it as some constant c. And now, if I want to solve for y, I just simply need to multiply both sides by e to the negative x. So I'll get y of x equals, if I multiply this first term times e to the minus x, I just get the 2x, because e to the x times e to the minus x becomes e to the x minus x, or e to the 0 or 1. 2x, this becomes minus, and then 2 e to the x and e to the minus x again, it's just 2, and this becomes plus c e to the minus x. And so I have a single parameter family of curves in C, but I have a condition imposed, so I should be able to solve for that value of c. So tell me that when x is 2, y is 2, so let's see. If I plug all that stuff in, I get that 2 equals 2 times, we know x is 2, minus 2, plus ce to the minus 2. So this gives me 2 equals 4 minus 2. So I get, if I keep this going, I get 2 equals 4 minus 2 is just 2 plus c e to the minus 2. And if I subtract 2 from both sides, it should be clear that I'll get that 0 equals ce to the minus 2. And this guarantees that c must equal to 0. Because e to the minus 2 is a real number. There's no way that that's going to equal to 0. And if I multiply c times e to the minus 2, then the c must be 0. So since c is 0, now I'll just go back and write my y of x. So I get y of x equals 2x minus 2.